function is simply to keep the speakers on time. I've been told that they must each have half an hour and a quarter of an hour discussion, and then we're allowing a little bit of time for a changeover. And so, without further ado, the first speaker is Dr. Jim Baggott, and his talk is how an electron can be in more than one place at a time.
First up, some acknowledgements. I must thank Harvey Brown and Joe Ashbourne for inviting me to come along and open the proceedings at this conference here today. It's an honor and a privilege. I am a former academic scientist who, whether you want to call it escape or dismissal, for whatever reason, I chose to step out of academic life a long, long time ago, about 25 years ago. But something had soaked into my DNA by that stage, and science and thinking about science and puzzling over some of the finer points of contemporary theoretical physics kind of stuck with me. I was never able to let it go. And I deliberately chose, after I'd quit academia and joined Shell, International Petroleum, that I would commit myself to find whatever spare time I could to write about stuff that was going on in physics and in chemistry and in other disciplines as well. And I've been using that spare time whenever I can find it to write a number of books, articles, and so on. So I've been thinking and puzzling about the nature of quantum reality for a long time. That doesn't make me an expert, far from it. When Joe laid out the ground rules for this session this morning, she said, "Oh, Jim, just give me the whole history of quantum reality in 30 minutes. And I thought about that seriously for a second or two. You know that phrase, how do you eat an elephant? Do we know the answer to that, or can we speculate on how you might go about eating an elephant? I've never really understood it. Why don't you just order the salad? And that's what I've chosen to do. I'm not going to attempt to give you the whole history of speculations, debates, arguments about the nature of quantum reality in 30 minutes. What I hope to be able to do is to set the scene as best I can. A lot has been said, a lot has been written, a lot has been argued about on this subject. And it's an interesting question as to why, after about 90 years now, we still find ourselves locked in debate about the basic fundamental essence of one of the best theories mankind has possibly ever devised. So it's very, very interesting, and it forces us to confront that horror of horrors, the interface of where science meets philosophy. And I'm going to try to be as respectful as I possibly can to my philosophy colleagues. Now, having set myself this ambition, I wanted to really get us started by focusing on some basic things. Now, Joe did actually point out to me that we may have members of the general public in the audience here today. And please then understand that I've pitched my talk. There's no state vectors in Hilbert space in these slides. There's no esoteric language where I've tried to avoid it. I have. This is nuts and bolts. What is it that's at the heart or the root of the challenges we feel that quantum theory provokes? And I want to start by maybe just reminding you a little bit of the history of our understanding of the nature of light. There were dramatic transformations in our understanding around the early part of the 19th century. One of my favorite stories, and this could be the subject of a book, was the story of the prize that was announced by Pierre-Simon Marquis de Laplace in 1819, seen to be Francis Newton, or Francis answer to Newton. I'm not sure he ever really was, but that's the French for you. And basically what Laplace wanted to do was to go out and find someone who could give a theoretical basis for understanding things like diffraction and interference on the basis of Newton's corpuscular theory of light. So explain to me how we get things like two-slit interference using corpuscles, using particles of light. One of his colleagues, Francois Arago, encouraged Laplace to change a little bit the rules of the competition, opened it up a little bit more widely, and as a result, Augustin Fresnel was able to submit a memorandum, not explaining how light interference could be explained using corpuscles, but explaining how light interference could be understood using waves. Not what Laplace wanted. The memorandum was passed to Simeon Poisson, a more astute mathematician than Fresnel ever was or could be, and Poisson came up with an absurd result. If the wave theory is right, and if I use a circular obstruction and look at the shadow that's cast by that obstruction, right at the center of that shadow should be a brilliant spot of light as a result of interference, combining constructively to create a bright spot at the center. How ridiculous. Everyone should know that you cast a shadow using a circular obstruction, you're going to get a shadow, you're going to get darkness. Arago said, hey, why don't we look? And indeed, I can't imagine how cumbersome or clumsy the experiment would have been, but he looked, and indeed, it's now called Poisson's spot. And there it was. Now, we had to wait for Laplace to die. He was a fading force in theoretical physics anyway. But generally speaking, theories don't get displaced on the basis of evidence, despite what common comprehension says should happen. But this is effectively the explanation that we've been living with for a long, long time in terms of the nature of light. We just need slits that are about the size of the wavelength of radiation that is being passed through, preferably monochromatic. That makes the visualization of the interference pattern easier. And in fact, if this is a little bit of a clumsy animation, but you get the sense that as a result of wave peaks lining up with wave peaks, we get what's known as constructive interference, a bigger peak, but where a wave peak meets a wave trough, we get cancellation and we get darkness. So light and dark fringes are a direct result of wave interference effects, and we can understand that perfectly straightforwardly. Then we get to a couple of nature's dirty little secrets. Planck in 1900, he didn't want to. Planck was not an atomist. Planck believed passionately that matter is a continuous structure, not atomic. There is a reason Boltzmann committed suicide in 1906. Nobody believed him. Nobody believed his interpretation of the second law of thermodynamics. And in his investigations of black body radiation, Planck tortured thermodynamics a little bit, and he certainly tortured statistics a little bit, if not a lot. But out of it dropped an equation: energy equals Planck's constant times frequency, E equals h nu. And he coined the term quanta to explain that as far as at least the absorption and emission of light radiation was concerned, we could think about it as though absorption and emission was occurring in discrete units called quanta. Einstein, a bold force in his younger days, 1905, one of the 5 singularly incredible papers he published that year, said, actually, if we take that seriously, then let's investigate what happens if we assume not that just light is absorbed and emitted in discrete units, but light consists of discrete units. And of course, today, we call these discrete units photons, a name coined by Gilbert Lewis, a chemist, in 1926. So light waves, interference isn't going away from this. We're not back to Newton's corpuscular theory. We are in a situation where, well, somehow light can be both. It can be both wave and particle. Then, a prince, no less, Prince Louis V, Duc de Broglie, went further, and in his thesis in 1923 suggested that in fact Einstein's conclusion could be pushed a little bit further. Yes, light waves can also be thought somehow to consist of particles of light, quanta of light. But how about if we consider particles of matter consisting of waves? So light waves can be particles and electrons can be waves. Now that was the basis, there's obviously a lot more to it than that, but that was the basis of the foundations of quantum mechanics in the 1920s. About 1925, 1927, much of our current comprehension of what quantum theory is saying was kind of founded and debated around that time. Okay, that's fine, but then how should we look back at that two-slit interference experiment where instead of a light bulb shining monochromatic radiation through these two slits or holes, we actually take a situation where we have an electron gun from the back of an old-fashioned TV set, and we shoot electrons one at a time through this apparatus. What happens? Well, we can expect a couple of things. Our classical intuition might be that the electron must pass through one or other of the two slits. Fine. Then we'd expect a picture pretty much like the blue curve here. A concentration of impacts where the electron has hit the screen on the other side, corresponding to its passage, its trajectory through those two slits. Or could we expect to see an interference pattern? So it's a simple choice. If we do this experiment, electrons one at a time, through this apparatus, what are we going to see? There was a lot of, pressure is the wrong word, but there's a lot of a sense. We don't let go classical intuitions very easily. Classical physics is effectively the physics of kind of every day. It's the physics of driving your car. It's the physics of watching Andy Murray lose the semi-final of the French Open in 5 sets. It's the physics of snooker. It's the physics of every day. So we don't like that common sense understanding of the world to be slipping away just as easily, quite so easily as this. So it's up for grabs. But when we actually do the experiment, and this is why I'm calling this the essential mystery, because everything that comes in terms of what we argue and debate about the nature of reality at the quantum level comes effectively from this one experiment. So here we go. Here we shine an electron gun through 2 slits, and we look. Hey, and good news. We get individual points where electrons impact the screen one at a time. And that's perfectly in tune with our intuition here, isn't it? Electrons pass through one slit or the other slit, and they impact the screen, and as a result of that interaction, they register in the form of a little spot of phosphorescence or a little white blob. But then we wait patiently. Being scientists, we're good at that. And we allow a few more electrons to go through the screen. Okay. I'm not going to get too excited about this just yet. And then a few more. And then a few more. And then a few more. And by the time we're done, okay, it's a little bit fuzzy. It lacks resolution, we would say. If this were a TV picture, we'd be trying to adjust the set to get a bit better definition. But what we see, of course, is the interference pattern coming back. Now, how are we meant to understand this? This is the essential mystery. How are we meant to understand this picture? So, here's what we're faced with. If we treat each individual electron as a wave, then, kind of by definition, it's described by this magical thing called a wave function. It doesn't really matter what the maths looks like. It's a picture that looks something like this. The peaks in this picture represent peaks where the wave, the electron wave, has interfered constructively as it has passed through somehow through these two slits. And the troughs represent dark fringes. They're going to become dark fringes and represent areas where, as a result of destructive interference of the electron wave as it passes through both slits, it won't appear on average. And that gives us rise to the black bars that we see in the interference pattern. Now, before measurement, the electron, notionally, passing again through this apparatus one at a time, is distributed. And this is really what I mean. I'm paraphrasing, I know. But this is what I mean by the electron being in more than one place at a time. Of course, an electron is never in more than one place at a time. But according to this structure, it has a probability of being detected anywhere where that function has a positive value. It has a probability of not being detected anywhere where that function has a low or zero value. Okay? So in that sense, we put an electron through this apparatus, and it has a probability of being found anywhere on the screen, pretty much, except for areas where we expect to see dark fringes. Okay. The difficulty with this is that if the wave function tells us that we have a probability of finding the electron anywhere where that function is positive, we know it's only going to be found in one place. So what quantum theory is telling us is that the wave function, the way we interpret it, is that there are many possibilities, there are many places the electron could be, but we know it's only going to appear in one place. And in order to get from there to the other side, we need to propose something that was probably most clearly articulated by the mathematician John von Neumann in a book that he published in German in 1932. It's called von Neumann's projection postulate. Notice the word postulate. Nowhere in the entire structure, the mathematical structure of quantum mechanics, is there a formula that tells you how that cloud works, hence the question marks. It's called the collapse of the wave function. It's the translation of a physical system where there is a probability for the electron to be in many different places, collapsing to a situation where it's going to be found only in one place. Now, we can have a bit of fun. Let's assume that the upper half of this screen is connected to a small vial of poison. And the whole thing is in a box in which we've placed Schrödinger's cat. Tony, I know, is going to talk to us a little bit more about Schrödinger's cat. I'm sure he'll illuminate us with much more detail than I can give you now. And let's assume that if the electron hits any part of the lower half of the screen, the poison is not released. We close the lid. We allow the electron gun to fire, one single electron. If it hits the upper part of the screen, the poison is released and the cat dies. Oh. If it hits the lower part of the screen, the poison is not released and the cat's alive. What happens? Well, in fact, it's interesting. Von Neumann was quite heavily influenced by mathematical physicist Eugene Wigner. And he suggested that, in fact, really it's only when we lift the lid and look does the wave function project or the wave function collapse. And the cat, having been in some kind of suspended state of aliveness and deadness, suddenly finds itself either one or the other. Now, Schrödinger, when he proposed this, it was very firmly tongue-in-cheek. He was pointing out the absurdity of this situation. Surely, folks, this cat is either alive or dead before we lift the lid and look. the physics must be over by the time we choose to look. Is the moon there when nobody looks? When a tree falls in the forest and there's no one out around to hear, does it make a sound? Yeah, these lovely philosophical conundrums, they're not physics. And they have no part in the way we want to try to understand the physical world. Now, all of this came to a head in a really rather excellent debate. I honestly recommend anyone with an interest in physics around this time to delve into various descriptions of this debate, including Bohr's own description. That's Niels Bohr on the left. Niels Bohr was the principal architect of something called the Copenhagen Interpretation of quantum mechanics. We're going to say a little bit more about that towards the end of what I have to say. And of course, the famous figure on the right is Einstein himself, who insisted, as a consequence of imagining the situation here where we have a collapse of the wave function and suddenly it's all down to chance as just exactly what's going to happen with the electron. And of course he insisted that God, as we know, does not play dice. Bohr came back, I think, quite legitimately. Surely it is not for us to tell God how he is to run the world. But at root here, in effect, is the nature of the way we seek to understand what's going on in this experiment, which I'm insisting is the essential mystery at the heart of the nature of quantum reality. Now, the Copenhagen interpretation sounds like it's something that really ought to be clear, nailed down, articulated in some reasonable form, but Bohr was actually notorious. He would slave over redraft after redraft of a paper, each redraft being more obfuscated than the previous one, tying himself in linguistic knots in order to try to be as clear as he felt he needed to be in order to explain what was going on here. He had allies. Heisenberg, my favorite Heisenberg quote is, we have to remember, it is not, when we do an experiment, it is not nature that we probe, but nature exposed to our method of questioning. Being very clear, confronting the philosophical issue at the heart of this debate. In effect, it really coming down to how we choose to interpret the wave function itself. Now, in what I'm going to do here, I'm going to oversimplify. I don't really make any apologies for that. I do think sometimes you need to get yourself out of the detail and take a step back and look at a problem from a distance. It's helpful if you can actually have conversations with people who have no background in physics or quantum physics and get them to be asking you questions. Well, Jim, how does that work? What happens? That forces you to try and find ways of articulating what's going on here in the clearest possible way. I do recommend it to everyone. How should we interpret this thing? At the heart of the Copenhagen interpretation, although it was never really clearly stated, was Bohr's notion of complementarity. Now, complementarity can mean lots of different things. Probably the best way to understand Bohr's notion of complementarity is in terms of waves and particles. Or if you want a modern political analogy, it's the complementarity between access to the European single market and the free movement of people. The British public is wrestling with that complementarity right now, which is why we have a minority government as of this morning. We want one or the other, we can't have both. The nature of complementarity is effectively telling us that the wave function is not real. We've got to let go all our hang-ups, all our tendency to want to interpret the stuff, the symbols, the concepts that we use in the mathematical equations that describe the physics. We have to let go our tendency to want to invest them with physical significance. Bohr was saying, The fact that you do an experiment over here, you get waves, you do another experiment over here, you get particles, means we can never know what an electron really is. Forget it. All we can know is what we see. Here it's a wave, here it's a particle. They're not contradictory, they're complementary aspects of the physical properties of an electron. So what does this then mean? Well, it means that the wave function is a kind of bookkeeping device. It's an instrument. It allows us to load in everything we know about a physical system, everything we think we understand about what's going to happen to it. There are all sorts of postulates of quantum mechanics, by the way, which really do reinforce or embed this idea that it's a recipe. It's like bookkeeping. You do it mechanically. You create a wave function in one basis, and if you have a different basis required to expose a set of potential measurement outcomes, you change the basis. You can do that, but it's still a set of instructions that you follow in order to get the right predictions. Probably the best articulation, modern articulation of the Copenhagen interpretation actually comes from Italian theorist Carlo Rovelli. In the late 90s, he published a few papers on something called relational quantum mechanics. Look them up. There are more recent papers published in 2005, 2007 or so about 10 years ago, with a couple of Rovelli's colleagues. You can get them on the archive. Look them up. They are really well worth reading. You don't have to believe what Carlo says, but here is, for me at least, the clearest statement of the Copenhagen interpretation that I've come across, and I've come across a lot. So the wave function doesn't collapse. There's no issue here. Carlo has a great phrase in one of his papers that says, this is no more surprising than the discontinuous nature of the change in my knowledge of China when I read an article in the newspaper about China. Lifting the lid of the box doesn't kill Schrödinger's cat, or not. We don't know the physical state of Schrödinger's cat. By definition, we can't know anything until we lift the lid and look. But if we want to have a prediction for what the state of the cat is likely to be when we lift the lid, we use the instrument provided by the wave function, the structures, the mathematical equations of quantum mechanics, and they will give us pretty much a good steer. This is a firmly anti-realist interpretation associated with Bohr and the Copenhagen interpretation. But I want to emphasize again, Bohr is not saying the moon doesn't exist when nobody's looking. That's silly. Well, it's not silly, but you know what I'm saying. What he's saying is that there's an empirical reality. Of course there is. But we shouldn't confuse what quantum mechanics is telling us here, what quantum theory is telling us here, with the interpretation of this as real physical states of the system. This is a device for conveying information which allows us to connect the past with the future. So he's anti-realist only in the sense that he's saying the concepts and the techniques we use in quantum mechanics are in themselves not to be interpreted as physically real. Now, his most famous statement, probably well known to you, is there is no quantum world, there is only an abstract quantum physical description. It is wrong to think that the task of physics is to find out how nature is. Physics concerns what we can say about nature. It's very strongly empiricist, even a touch positivist. But nevertheless, honestly, if I look back at all of the experimental research on the foundations of quantum theory over the last 2-3 decades, I don't like this interpretation. But I've got to tell you, there is something that is becoming increasingly irresistible about it. I don't like it. Now, we can go another way. And this, of course, was Einstein's position. Come on. We've been interpreting concepts in our mathematical equations describing the physics of the world with great success down the centuries. Why not continue to do that? Why not invest some physical significance in the wave function? So it's really telling us something fundamental about the underlying quantum physics. If we do that, if we're prepared to do that, then the wave function does do something really strange. Remember, there's nowhere in the equations of quantum theory, which for the physicists in the audience is effectively an acknowledgement that quantum mechanics, the wave function, is unitary. It doesn't change discontinuously. Left to its own devices, the wave equation evolves in time in a consistent manner, entirely cause and effect related. So the collapse of the wave function really is something strange, and therefore you cannot hope but to accept that quantum mechanics therefore cannot be complete, because we can't explain the collapse of the wave function, von Neumann's projection postulate. And that's a realist interpretation. Again, not in the sense that we believe there is a reality, a fundamental reality, but we're interpreting the structures, the concepts we use in quantum theory in a realistic way. Now, I still think this is by far the best Einstein quote which summarizes Einstein's realism. I have no better expression than the term religious for this trust in the rational character of reality and in its being accessible to some extent to human reason. So let's be absolutely clear. When we start to speculate about the physical significance of the wave function, we are, in ourselves, whether we know it or not, investing in an article of faith. Did you realize that? Perhaps not. So, this antagonism between anti-realist and realist interpretations, the trouble with this kind of instrumentalism on the left-hand side is that I believe, personally, and have done for many, many years, it's rather sterile. It doesn't tell me, it doesn't convey any real understanding. Don't get me wrong. The theorists who are using quantum information, working on quantum computing, doing quantum cryptography, they don't much care about this subtle philosophical debate. They know that quantum theory works and they use it day after day, and it works. So when I say understanding, I don't mean understanding of how to use it, I mean understanding of what it means. So, if we turn our backs on this as being empty of any real insight or explanation, it doesn't tell me a little bit about how the world is working, then we've got no choice but to play the game of theories. And this is actually probably the most important point I want to make this morning. Playing the game of theories comes with some consequences. This, by the way, it's seen from an unusual angle. That's the Strait of Messina between Sicily and Italy. It's famous. And sailing on this sea is the ship of science. Now, we are caught between the Homeric equivalent of a rock and a hard place, because on the one side we've got Scylla. The rock shoal of Scylla is the instrumentalism, consistent with the Copenhagen interpretation. It's empirically, factually correct, but it's empty of understanding. Not in terms of how to apply it, but in terms of what it means. We can go no further than a belief that the Copenhagen interpretation is effectively the only interpretation. The danger that we've got is, of course, on the other side, we've got the whirlpool of Charybdis, which I've articulated here as a whirlpool of wild, unconstrained metaphysical nonsense about reality. And when we play the game of theories, what of course we're trying to do is we're trying to navigate between Scylla and Charybdis. We want to, if we're scientific in our approach, we want to be able to nail the theory back to the rocks. We want to bring it back to empirical reality. We want to do a test. We want to do an experiment. We want to make an observation, whatever it might be. That's what we want to do. The danger that we've got and the difficulty that we face is that Charybdis is very tempting. And it's my firm belief that some theorists set sail for Charybdis a long time ago and then abandoned ship. And we may hear some results, consequences of some of that kind of speculative metaphysical discussion again later on today. And the only reason for telling you this is to understand the nature of the game that we're playing here. We don't like the rock shoal. That's harsh. That's empty of real meaning. But at the same time, I'm not sure we like the whirlpool either. We want to try and navigate the way. Science has always worked by navigating the way in between. And we should probably just remember what Odysseus himself did. He made sure that he sailed close enough to Scylla because he reasoned that it was the only risk sailing too close to Scylla is you lose a few crew members. Sail too close to Charybdis, you risk losing the whole ship. Okay? That just about sums up everything I wanted to say. So, literally to recap, 1 minute, George, is that okay? Literally to recap. I've got whole shelves of books back in my study at home, all about the interpretation of quantum mechanics. Loads of them. And these are, don't get me wrong, excellent books, many of them. They tell you an awful lot. There's a lot you can learn from them. But at heart, the essence of the nature of the debate, I believe, is caught in the essential mystery of the two-slit experiment with electrons. The collapse of the wave function, Schrödinger's cat, the great Bohr-Einstein debate, all flows from an understanding that what this is really about is how we seek to interpret the symbols in the mathematical equations of quantum mechanics. We can go two ways. The minute we give up on the Copenhagen interpretation and says there must be more to reality than this is the minute we have to figure out how to play the game of theories. Playing the game of theories, I believe, is about how you navigate the Strait of Messina between Scylla and Charybdis. The rock shoal of instrumentalism against the whirlpool of metaphysical nonsense. We just have to make a decision where we're going to play, in the hope that having done some speculative theorizing, we can get back to empirical reality eventually. George, thank you very much.
Jim, thank you very much. I very much appreciate your emphasis on the two-slit experiment because in my experience, quite a number of high-ranking quantum physicists do not take it seriously in the way that you did. We now have 15 minutes for questions. So,
thank you for a wonderful talk.
Thank you very much.
As you emphasized, Heisenberg, Bohr, and others essentially decided that the wave particle problem didn't have a solution, not going to be able to solve it. And so they developed quantum theory as a theory about the results of being measured. Clearly avoided to solve the problem. But supposing you take the view that what quantum theory is really trying to tell us is that the quantum domain is fundamentally probabilistic. Probabilistic transitions really are going on objectively in the world. Then, the classical quantum wave particle problem turns out to be the wrong problem. Because particles, waves, or fields are really entities of deterministic classical physics. If the quantum domain is fundamentally probabilistic, then we're going to have entirely new kinds of fundamentally probabilistic entities. Indeed, exactly the sort of entities that quantum electrons and photons seem to be. And the key problem then becomes to specify precisely in quantum mechanical terms what the conditions are for probabilistic transitions to occur, measurement being a special case. So that seems to me to be an obvious option, which completely got ignored because the two parties in the great debate were between abandoning realism and abandoning determinism, and holding on to realism and holding on to determinism. And no one really explored the option realism, but probabilism.
Yeah. To be fair to both protagonists in the debate, Einstein's was a probabilistic interpretation. He didn't deny that if you wait long enough and patiently enough for the electrons to go through this two-slit apparatus one at a time, you'll get an interference pattern. That can only be explained in terms of some kind of wave model. But Einstein's interpretation of probability was very different. Einstein saw this as statistical probability. The electron goes through one or the other slit and something happens to it. It maybe follows a pilot wave. He played with that idea for a little while in 1927 before he gave up on it. So you have this situation where I think the essence of probability was very much there, alive in the debate. Maybe it did indeed get overshadowed or overlooked, but it was the interpretation of that nature of that probability. Now, quantum probability is very distinctly different from anything we've ever seen before in physics. So, to a certain extent, that's true. I will answer the question slightly differently, if I may. Thinking deeply about this for as long as I have, maybe what the probabilistic nature of quantum mechanics is actually telling us is indeed what Carlo Rovelli is saying in relational quantum mechanics, what the Copenhagen interpretation taken at face value is telling us. And that is, we've been kidding ourselves all this time. You write force equals mass times acceleration and you know what that means. But you go look for Newton's definition of mass in the Mathematical Principles of Natural Philosophy. It's a circular definition. Mass is density divided by volume. How do you define density? Well, it's the mass of a unit of volume. So you're in a situation where, in fact, taken at face value, if we look at it hard enough, all the equations of classical mechanics are instruments, which we use quite simply to tell us what will happen when we look at the situation in the past and we want to predict what might unfold in the future.
That's very, very, very you know the troughs on that picture you showed us, are they ever zero?
I think, in principle, yes. Theoretically, no. There's always some fuzziness in the way that experiments are done. There's always some error. And that's why you see the issue of resolution coming through the two-slit experiment.
I think if you use a crystal it's very good.
It's possible to get it close to zero, but probably you'll never get it perfect.
So what does that mean?
Well, what does that mean is effectively the way that we think idealistically about the way the experiment should run is never how it actually happens in the real world. Things have edges, things are fuzzy around the corners, and all that kind of stuff means that the principles are correct. We're getting the correct prediction, but don't expect it to be 100% accurate.
Would it be if you run it forever?
No. No. Okay?
Could you say just a bit more about quantum probability? Sorry to press you on that, but you know someone has to.
Let me then maybe go back to the answer I gave here. So Einstein had a way, he attempted to try to interpret what was going on in an experiment like this in terms of a statistical probability. So he didn't really try to identify what was happening to each trajectory of the electron, if you want to think about it like that. But for some reason it was being guided or steered into a region which then statistically gave the appearance of wave interference effects. The nature of quantum probability is different. You can think about it in the context of an electron wave like a light wave, or you can think about it in the context of a quantum field, an electron field in quantum field theory. Somehow you've got this extended, if you take it seriously as a physical description, you've got this extended structure. It's spread over a distance. And the nature of quantum probability is that, you deal with a single electron, you pluck a single electron from the electron field, there can only ever be one electron in one place at a time, despite what the title of my talk says. And so the nature of quantum probability is that you just simply cannot predict where that electron will manifest itself. You can only calculate the probability that it can be in these different places. And that's very, very different understanding of the nature of probability.
Yes, it is. So it's more like superpositioning. You're almost attaching the quantum probability
But yeah, you can understand it in terms of a superpositioning, of course, yes, and that effectively that wave function description is a superposition of the wave functions spreading out beyond the two slits. So yes, absolutely.
Okay, I have a comment on also the first question about probability as an intrinsic feature of quantum mechanics. I agree that there was this big debate, but in the shadow of the big debate between these two opposing bunch of people who discussed this, there is development, and I can recommend the book to you. It's by Stephen Adler from Princeton University. So he's a theoretical physicist. He's very popular in high energy physics, and he worked on something which is called trace dynamics, which he thinks is an underlying theory which is more fundamental, if you want, in quantum mechanics. And what we see as quantum mechanics is some sort of a thermodynamic limit, of this underlying theory. So the underlying theory explains the stochasticity, the probability which we see in quantum mechanics, which is effectively described by the square root of the modular square of the wave function. Yeah?
Can you ask a question, please?
Okay, sorry. No, I just wanted to recommend the book.
Okay.
Thank you for absolutely exciting presentation today in a form I haven't heard before in quite that way. I just wanted to recommend a book and also suggest a direction to which it may point, which you've certainly taken us along today. And that is that there isn't a great problem that we perhaps have thought between bringing a conversation between the sciences or physics and philosophy. But in fact, your great picture of the Scylla and the Charybdis was enunciated by Austin Farrer, who was head of the Keble College here many years ago, showing us that to go for a metaphysics rather than the empirical was mistaken in both ways. That we needed to bring together theory and practice and stay on the ship and not lead to suicide.
That's fine, if I may respond just very, very quickly. That's fine for as long as you have experimental data or observations that are telling you what you're doing wrong or what you're doing right. Right now, in whole swathes of frontier theoretical physics, we don't. Everything that we understand about the nature of the physical world is captured in two standard models, the standard model of particle physics and the standard model of inflationary Big Bang cosmology. Lots of debate because we know these aren't the end. There's lots of explanatory gaps. But where to go from here, you've got no choice but to play the game of theories. You have no choice. And I don't think that's wrong. I think how we play the game of theories, though, needs some careful consideration.
Well, could I just recommend the book? It's Questioning Causality by Ron Harry and F.M. Mogadam. And I think that is going to help you map the philosophy for physics that you've delighted us with today.
Thank you. I've got one of Ron Harry's books somewhere on my shelves.
Jim, Jim, thank you very much. That was a very brave talk, I think. I think you sort of did summarise it very nicely, and I think you were very respectful as well, which is even more astonishing. But I've got a very simple question. I mean, in the double-slit experiment, which I agree is at the heart of it, it highlights a very, very important central component. Yeah. What if you have a measuring device? I suspect, as you know, the interference pattern disappears. Yeah. And I'm just thinking, how does relational quantum mechanics interpret that within that framework?
But very simply, you change the nature of access to knowledge. So the basis of relational quantum mechanics is literally it's relational. So it's always relative to the system that you're observing or you're doing experiments on. What Carlo is saying effectively is that we can only speculate about what is really going on, but if we stick to what we know and can empirically verify, then looking to see which slit the electron goes through changes the nature of the relationship between the apparatus and the physical system beneath. And you'll get a different result. The interference pattern will wash out and you'll get a particle. Best summarised, by the way, if you haven't read it, is Tom Stockart's play from the late 1980s, I think, called HAPP, where you've got complementarity in the form of a double agent.
You mentioned briefly, hidden variables. 27 sort of. But in fact, as you obviously know, in the early 1950s, David Bohm brought his work into, and in fact had great impetus with John Bell and his work. So I don't know.
I overlooked all of that entirely, so thank you very much for the question. It was something that I was going to slip in, although there was nothing necessarily on the slide. So this is the nature, again, in terms of the game of theories that I've been talking about, and fixing the missing pieces in quantum mechanics by adding hidden variables, whether they be local or crypto non-local, as Tony Leggett has worked on. What these do is that they do steer quite close to Scylla. We speculate. Hidden variables are objects of metaphysical speculation. If you want to think about them that way, that's fine. But we stick close to Scylla because we bring back what the hidden variable version of quantum mechanics predicts, and those are predictions that we can then look in a laboratory to find out whether they're borne out or not. The intriguing thing is that over the years, and this is why I say I fear, we might just have to suck it up and accept that relational quantum mechanics or the Copenhagen interpretation it's uncomfortable, I know, but maybe it is indeed telling us that this is what we've got to learn to live with. But I'm all for playing the game. Do the speculation, but connect it back wherever you can with empirical reality.
Jim, thank you. I think we're going to have to wrap this up now. So thank you very much indeed for that. Very interesting talk. I'm just going to make two comments. One is that you didn't mention the transactional interpretation of quantum mechanics, which I find very interesting.
Right.
And the other one is that I think the reason that a lot of quantum physicists ignore the two-step experiment is because basically in their work they only deal with statistical context in which it doesn't matter what the individual one, but there are some contexts where the individual dots matter. One of them is inflationary theory in the early universe, where you're supposed to have quantum fluctuations which eventually lead to seeds on the large scattering surface which come into our galaxy. And that is where the individual dots actually matter.
On a cosmic scale.
On a cosmic scale. Okay, we've got to change over. Tony.